Hey there, and welcome to the second video that I'm making about rate of change, average, and instantaneous in regards to how we're going to be looking at it for calculus. And what we see here is an example problem. It's a word problem. And the table that you're being provided is, something to help you kind of organize your thoughts for your notes, but it's not something that we're generally going to be given, but we do need to be able to read the question and see what is the important information and what are we trying us to do. So the question is saying, what is the instantaneous velocity? Oh no, I didn't mean to do that. What is the instantaneous velocity of something that is dropped, a coin in this case, at the time of 0.7 seconds? Now this goes back to a famous experiment that Galileo did a long time ago. He would kind of be up here in the Leaning Tower of Pisa, and he would drop like a hammer, and he would drop a feather, and I'm not a very good artist, and he would say, well, they should be able to fall at the same velocity, giving us this function here. And we want to know, well, what is the instantaneous rate of change for some object, the coin in this case, as he drops it from some height of some kind. Maybe he is at the Leaning Tower of Pisa. So what I would typically do in class is I would say, well, first of all, the first value is given to you, 22.56, and in this case it would be feet per second. So what I want you guys to do first is take your calculator, whatever you're using for your calculator, and make sure, can you calculate the 22.56, because if you can, then we can move on quickly. Otherwise, you need to get a little bit more explanation on how we got it. So go ahead and pause the video now, make sure you can get that 22.56, and when you got it, come back. Or if you can't get it all, then come back also, and we'll still show you how to do it. So go ahead and pause the video now and make sure you can get that. Okay, so hopefully you've gone through the process of playing around with the numbers on your calculator and saying, okay, well, I want the rate of change of the position that it is in time, and of course then we need the difference of the time. So we're looking here at like delta P over delta T. We're still talking about change in position over change in time. So here we would say something along the lines of P2 minus P1 over T2 minus T1. Okay? Well, given the function that we have, in this case, we would express it as 16 times 0.71 squared minus 16 times 0.7 squared divided by 0.71 minus 0.7. And that's how we're going to get the average velocity over that time interval. Now here, this is an average velocity. We want to try to estimate what the instantaneous velocity is, so we're going to make that time interval in the denominator smaller and smaller and smaller so we can get a good approximation of it. Right now in the first example, 0.71 minus 0.7 gives you a difference of 100ths of a second, but in the big picture, that's not a big difference. So now that you've had an opportunity to see how we came up with the 22.56, you can find the next four values in the table and see that as the time interval gets closer and closer and closer to zero, it gets smaller and smaller and smaller. And at the bottom where it says t is equal to 0.5 seconds, that's a typo. It should say 0.7 seconds. But we can estimate that over time, at that time of 0.7 seconds, that the coin is falling about 22.4 feet per second. And that's how we would approximate the instantaneous rate of change by getting the denominator closer and closer and closer to zero. Now visually on a graph, what is the difference between the two? What does average rate of change look like? And what does instantaneous rate of change look like? And this is what we see here. Here I have a line that's going through 2 points along a curve. And because it's going through two specific points, we refer to that as a secant line. And I want to know the average rate of change between those 2 points. Well, the average rate of change between those 2 points is just going to be the slope of that secant line. So I want to know what are the coordinates there. We have one coordinate at A, which is 1, 3, and one coordinate at B, which is 4, 4. And so I plug those equations, or plug those numbers into the slope formula, find the slope of the line, or the average rate of change, and I would say 1/3. Pretty straightforward. And that's what average rate of change looks like. It's the average rate of change between any 2 points along a curve. Now for instantaneous rate of change is going to be tangent to a line because it's only going to be evaluated at a single point, not in 2 different places. Now in reality we have to evaluate it in a couple of points because we have to have some time interval that's not 0. So on the graph that's provided in your notes, I've conveniently drawn this line here so that way I can have some points that I can use. I've selected 0.56 so that it looks pretty much along a line that would be tangent to the curve at point C. So I have a point at C at 2, 4 and a point at D which is 5, 6, and again I find the rate of change between those, the slope between those 2 specific points, the slope of the tangent line, giving me my instantaneous rate of change, in this case, of 2/3. So again, we're going to go ahead and pause here for this one. This will be the end of the second video, but graphically that's what the difference looks like between average and instantaneous rate of change on a curve. Average is going to go through 2 very distinct points along the curve itself. Instantaneous will be using just a point along the line where we'll have a line tangent to the curve. But let me know if you have any questions about anything you've seen in the video, and I'll be happy to answer them. Until next time, we'll go on to the next video from here, and thanks for watching.